Hi, can everybody hear me? Yeah. Okay, so TensorFlow. Let's see a show of hands. Who has heard of TensorFlow before? Pretty much everybody. Okay, good. Who's actually used TensorFlow before? A good part of you, maybe half, something like that. That's good. All right, that'll help. If you've used TensorFlow, if you've used, who's trained a machine learning model before? Okay, similar, maybe a few more. Okay. Has anybody actually worked with TensorFlow Extended, TFX? Okay, I got two. That's good. That's good. There's usually very few people who have because it's pretty new, and that's why I'm here, is because it's new and we want to talk about it. So, let me get my clicker here, and let's get started. So, if you've trained a machine learning model before, then you're well aware of models, right? There's all different kinds of models, convolutional neural networks, recurrent neural networks, fully connected, what have you. There's a lot of different architectures, and that's usually what we focus on. That's what the research papers are written for. They talk about the models and the architecture and the result and the data. So we tend to focus on the ML part of things. But when you go out and you're going to take that great work that you've done in creating a machine learning model, and you're going to try to apply it in a real-world situation to deliver a solution that someone's actually going to use, there's a lot more you need to think about. There's all the things that make a production solution. And when we're talking about software engineering, that's modern software engineering methodology. So all the things like testing and deployment and integration and monitoring and all the stuff that you do for software solutions. So an ML pipeline helps you move from coding up a model with the data set that you have for training, or if you're doing unsupervised, and moving that into a production environment where you're going to deliver a solution that's going to be reliable and dependable and maintainable. A pipeline like this is pretty much the way that people do this. So you start with data ingestion. You're going to take in your data. Then you're going to analyze it and verify that you've got values in all the columns you expect to have values, that they're the right kinds of values, that if you're talking about a categorical variable, that it's within the categories that you expect to see. If it's text, that it's actually supposed to be text, or if it's a number, that it's actually a numerical value that you can parse out. And then you're going to apply feature engineering. And feature engineering will help you take the input data that you have, try to extract the most predictive information that you can get from it, try to do any dimensionality reduction that you might want or need to do or can do. And then you're going to move to training. So we've gone all the way to here before we got to the part that we were thinking about in the first place. That's where we actually hit our model. When we're training, and tuners help us do that. Tuners help us with the problem that you have, you're probably all familiar with. You've got to adjust your hyperparameters to get the best results. Then you've got some kind of result, but how good is your result? Well, typically you look at a top-line aggregated metric, right? Like, what's my AUC across the entire data set? That's great, except it ignores the fact that individual slices in your data set can have very different performance. And those individual slices can be very important. So for example, if what you're trying to do is predict when a hurricane happens, there's a small slice that is hurricane conditions, or when an emergency happens. Or if you're looking at a set of people, and a very small slice of those people is buyers. So slicing and understanding the performance of your model across different subsets of your data is very important. And that's what you're going to do in model evaluation. And then finally you get to the serving, where you're going to actually respond to inference requests. And logging is part of that as well. Now, along with this whole thing, you've got configuration management that you've got to do. You've got garbage collection. You've got to control data access. All that stuff comes with a production solution. So, how does this connect to TensorFlow? Well, it connects with TensorFlow Extended, TFX. And TFX takes that sort of pipeline architecture and it implements each of these pieces. So there are libraries that we have open sourced that are used within Google, and those are used in each of these stages of the pipelines. These are actually used to implement pipeline components. And we'll talk about what each of these is and what the components are and how data flows through. Along with that, you've got job orchestration. So as you're running a job, you've got to coordinate the processes that you're running, the components that you're running, along the pipeline. And orchestration is how you do that. It's how you define the pipeline as well. TFX is used and has been used for several years within Google for a lot of our stuff. Within Google proper and within the Alphabet companies, it's used all over the place. So we have a fairly long set of experience, a fairly high degree of confidence in the code that we're open sourcing for the community to use. And we have partners as well, people like Airbnb and PayPal and Twitter that are using this now, and they're using the open source version of this. So this is what we're going to be talking about. Part of this is more relevant to a Flink audience because it's based on Apache Beam. And Apache Beam is a unified batch and stream distributed processing API. So you can run batch jobs, you can run stream jobs. Within TFX, we mostly run batch jobs. We pretty much only run batch jobs in the open source version. There are a set of front ends, though, and we'll talk about that. So once you have coded to a Beam API, you can apply that to a number of different platforms, including Flink, but also including Spark and others, and different languages. So Beam gives you the ability to run in Go or Java or Python. We're using Python. So those runners, including Flink, are available. So why do we do that? Because when you're implementing a machine learning pipeline, you're rarely going into a greenfield environment where you're going to start from scratch and you're going to produce the pristine design that you all want to do. Usually you're starting from an existing deployment of something. You might be using Spark, you might be using Flink, you might be using something else. So rather than force you to move to an entirely different cluster or an entirely different platform, it's portable. It'll move with you to the platform you likely have. Depends, if you have something really obscure, but in general, it has most of the ones that you're going to be wanting to use, including Google Cloud Dataflow if you're running on the Google Cloud. The portability framework within Beam allows you to run your language of choice. And there's also a side benefit. You can leverage things written in one language and access them or invoke them from another language. So we'll talk about that a little bit. This is what the components look like and how they map to the libraries. So when you go to the repo on GitHub, what you'll see are libraries, and you'll also see components, but they're not really as visible because they're not at the top level. So data ingestion is it's a component called example gen. So that's going to take in your data. But then we start to use a library called TensorFlow data validation to do three different components here. Statistics gen is used to look at your data set and calculate statistics across it. So what's the mean? What's the median? What's the standard deviation? All those things to try to understand what your data set looks like at a particular point in the life cycle of your pipeline. Because remember, you could be starting a new pipeline, or you could be deep into a running pipeline. Schema gen is looking at your data set, and it's figuring out the schema of your data. So Is it a float? Is it an int? Is it text? What are the different types of your columns? An example validator is taking those two results and it's going to try to find anomalies in your data set. So missing values, a float where you should have an int, text where you should have a number, that kind of thing. Oh, sorry. We'll go through some of the rest of this as we go, but basically TensorFlow transform is used to do the feature engineering part of things that we talked about. So you're going to use that to do things like feature crosses or create vocabularies, the typical feature engineering types of operations, PCA. Trainer is where we're going to get to actually taking a TensorFlow model and training it. So evaluator and model validator are used once you have trained your model and you have a result. Evaluator is used to do the kind of slicing that we talked about, and that's using TensorFlow model analysis to do that. Model validator is involved in the deployment process. So once you've evaluated the performance of your model, you want to make sure that the model you're going to deploy now is at least as good or better than the one that you already have deployed. Because you don't want to get into a situation where you deploy a new version of your model and suddenly the performance goes crazy, right? So this is a production system. You might be on iteration 5 of your model. And pusher is the actual deployment itself. That's where you deploy into your target. So what makes a component? I've talked about all those different things that are components. What is a component? So it's a packaged binary or a container. And it has well-defined inputs and outputs. So those inputs and outputs are metadata and artifacts. There's a well-defined configuration, and in this case, it's Python. And there's a metadata store, which is really key to making all this work. That's going to store the input and the output from each of our components, as well as the lineage for that and the history. So you can go back in time and look at comparing one model to the next, or 5 models in the past, or what have you. That's context. So the way this works is you've got a component. It's going to insert metadata into the metadata store. The data itself will be put somewhere else. It's just the metadata. And other components are going to pull out of that, read from it. The deployment targets that you could be targeting for your model depend on really what you want to do with it. So you could be going to TensorFlow serving to serve online. You could be going to TensorFlow Lite to serve in a native mobile application. You could be going to TensorFlow JS to serve in a web browser or in a Node.js application. You could even be publishing into TensorFlow Hub to share your model with someone else, or to just store it for you to use in other contexts. Or you could be doing all of that. The thing that gets you to this is a saved model format. So once you've gone through the pipeline, the end result that you're going to deploy is a well-defined protobuf-based format called saved model. And that's universal across the TensorFlow world. So, metadata store. This is actually kind of new. We just announced this at the TensorFlow Dev Summit. Anybody go to the TensorFlow Dev Summit? No? Yeah, well. Well, so you can think of these kinds of pipelines in a couple of different ways. You can have a task-aware pipeline where the result of the previous task triggers the next task. Or you can have a task and data-aware pipeline where each of the tasks creates artifacts within the metadata, and they're aware of the metadata that's been created by other tasks. So when things get triggered is really based on what that component knows about the metadata and what its requirements are. It's a more fluid type of system, more fluid sort of flow through that pipeline. So what's in the metadata store? Well, artifacts are the big thing. So artifacts are things like the models themselves, the data at different steps in the pipeline. So if you've transformed your data with feature engineering or what have you, that's an artifact that's going to be stored. And evaluation metrics, when you've done evaluation or you've created a schema or you've calculated statistics. Then there's records of execution. So you have this history that you start to build up of, I've run this component, here was the result, here's when it ran. And then the next time it runs, that's the next point in that history. And that's lineage tracking. So across all the executions, a good use case for this is when you see a problem or you see something that you like and you want to track it back in the pipeline to figure out where did that thing start. In other words, if I had a problem and I detected it here, did it actually start back here? Or if I see a result I really like here, was it generated because of a different result here? So lineage tracking is really important. So this is the kind of thing that you can pull out where you're getting the number of steps, you've got the checksum, it's all the characteristics of particular runs. And you can display that as a graph. So, in terms of visualization, you can start from where it was created and trace back. And this is something that you get when you run in a notebook under TFX. This is one of the frameworks that you have. This is another one. This is based on a library called Facets, and this is looking at statistics of your data. So when you've run your statistics gen and you're looking at what your data set looks like, it gives you things like the histograms and the mean and standard deviation, all that stuff. So you can really dive into your data, in a nice, friendly visualization and see what's going on with it. And some of this, can be pretty important. You may have a feature where you have a lot fewer data points than you thought you have and a lot of empty rows. So you want to be able to look for stuff like that. This is looking at model performance. So I'm slicing the model. I'm looking at the example count here. And I'm looking at different values for that particular example. So hour 1, hour 0. I'm trying to understand different parts. And you'll see how much variance there is, which you would expect to have. But there could be situations where that'll show you something that you didn't expect or that you didn't know about. One of the things that you have to be careful of is values like that where you don't have enough examples, and really when you're trying to train to predict those values, your loss surface is so sparse that it's going to be hard to make a good prediction. TensorBoard, if you used TensorFlow before, you're probably familiar with TensorBoard. It's a great way to visualize what happened in the training process of your model. So you can look at an individual model run like this, or multiple model runs and compare them. So again, it's a nice visualization tool to have for this. And you can compare the statistics for multiple data sets or multiple iterations of your data set, because remember, we're going to a production environment, so this is going to live for a while. There's a life cycle. You're going to probably get new data that you're going to add to your training set. You may end of life some other data if you feel that it's really expired in terms of its predictive quality. So understanding the difference between those data sets is important. So the types of things that metadata gives you are the kinds of things that we talked about. You have a lineage tracking that you can apply to try to understand what happened with a particular artifact. You can compare previous model runs. You get carryover states. So if you've started to train something and you've stopped, you can, instead of starting from the beginning, you can warm start and continue that training. And reuse previously computed outputs. What that essentially means is caching. So you've run a component, you've generated a result from it, and you're going to continue through the pipeline. Rather than rerunning that component and generating the same result again, you just cache it. Okay, so how do we orchestrate TFX? These component things that we've talked about have drivers and publishers. The driver supplies metadata to the component, and the publisher takes the result of the component and puts it in metadata. The thing in the middle is where the work is done, the executor. That's where your user code is going to be implemented. The driver and publisher, you pretty much just get for free, and you're just going to leverage them. On top of that is a config, and that config in TFX is Python-based. So we'll see what this looks like. Many of the components, and we'll go through the ones that we're talking about, run on top of Beam. If they're processing a lot of data, and we have a lot of situations where we have terabytes of data that we're trying to run through, a pipeline distributed processing engine is important to try to work through that data. And Beam gives us a portability layer on top of many different pipeline processing engines, including Flink and including Google Dataflow. Some of the components, actually one of the components, well, no, I take that back. There's more than one, but the main one that uses TensorFlow itself is Trainer. There's also Transform uses some TensorFlow as well, and so does Evaluator. But as far as the big TensorFlow model thing, that's Trainer. And other components are really just user code. They're just Python. So Pusher, for example, is just pushing out the result to whatever deployment targets you want to look at, and that's really just Python. So here's some code. So remember I said that configuration is in Python. Well, this is configuration. So we have create pipeline. We're going to define what the pipeline is. And you can just see how things flow through. You start with examples. You have a component called example_gen that's going to read from that. That's going to flow into statsgen. And at some point down here, you get to transform. So transform's taking the examples that that have run through your statsgen and your schema_gen and so forth. And it's going to read those in, and that's going to do the transformations, the feature engineering that you want to do on your data, and so on. So that's the configuration. It's not YAML or anything like that. It's just Python. An executor, remember when we looked at components, there's that middle piece that is really the part that you own. That's the executor. And an executor is going to take input from a driver. It's going to write output to a publisher. But in this case, we're using Beam to do a bunch of processing. So we have Beam doing reading from TF record. We're generating statistics with it. This syntax it's Python, but it's Python with some overloaded operators. So you see the pipe operator that we're using at the beginning. Part of what Beam gives you is this syntax. So what's really different about that is the pipe operator and these chevrons. So back to orchestration. We started to talk about that, then we kind of took a little detour. Let's continue with that. So there's different orchestrators that are out there that people are already using. And rather than force you to choose another one, our approach is to try to be agnostic. So currently we have Airflow and Kubeflow as implementations, but you could take this and run it with Argo or whatever orchestrator you like. So that's what really wraps that pipeline and orchestrates the flow through it. Yeah. So you get things like this. This is what the pipeline DAG, or directed acyclic graph, would look like in Kubeflow. That's what it looks like in Airflow. So when we put all this together, this is what a DAG looks like at sort of a graphical level. Things flow through. Example_gen flows to statsgen, flows to schema_gen. We evaluate. We're going into transform, trainer. evaluators kind of off to the side generating your model performance results, and through validator and pusher, and finally our deployment targets. So you could be going to any of those or all of them. So let's take a look at individual components. This is example gen. In this case, it's taking either CSV or TF record. It's producing a result and doing the training and testing split. So that's what the code looks like. That's the whole config for example gen. Stats gen. This is what's producing the statistics that are behind the visualization that we had to understand our data set. That's what the whole configuration looks like for stats gen. This is what, this is, again, that same kind of visualization is highlighting a particular feature where you may have some issues. Schema gen, which generates the schema for your data, what types are your columns, what types are your features, is really simple. Takes the result from stats gen, flows through, produces a schema. Now it's going to infer the schema from your data. So it's going to look at your data and say, this feature looks like it's a float, and this feature looks like it's categorical. But once it's done that, once it's done the inference, you can then adjust that schema to make changes that you, with your domain knowledge, know that you need to make. So, for example, you may have a categorical feature where not all your categories are represented in your training set, but you know that there are other categories that you may hit. So you could add those. Example validator is going to take the results of StatsGen and SchemaGen and just look for problems in your data. So it's going to make a pass through your training set and try to identify any problems that you may have had so that you know about them and generate an anomalies report. Transform, where we do our feature engineering, is a little more complex. This and trainer are the ones where there's probably the most complexity in terms of the code. The configuration is pretty simple. So that part, as far as defining it in your pipeline and defining the ins and outs of it, that's pretty simple. The code itself is where you're doing your feature engineering. So that can get pretty complex. There's a lot you can do in feature engineering. The TensorFlow transform library gives you a lot of transforms that you can use. So, or you can just write Python to do things too. So there's a lot you can do there. And depending on how sophisticated you want to get, that code could get fairly complex. What it's doing in transform is two things, really. So one, it's making a full pass over your training set, and it's calculating things that are going to be summary statistics. So things like the standard deviation, at the end of the day, you're going to end up with a number. That's your standard deviation of your data set for, say, a particular feature. So it's going to take a result like that, and it's going to insert it in a TensorFlow graph as a constant, because it is a constant. It's one number. Other things, it's going to insert into the graph as an operation. So that operation is going to happen with each new data point, each new row or example that your model sees. And then that subgraph gets inserted into the model that you train. So the result of that is you're using exactly the same code to do training, and when you publish your model out to serving or your mobile app or your JavaScript app or whatever it is, it's using exactly the same code. And that's important because if you're using two different sets of code to try to do the same thing, maybe they do the same thing, maybe they don't. You can have a problem with what's called training serving skew. So you want to avoid that. You want to write it once. And that's what transform gives you. Trainer is, again, where the TensorFlow model really lives. The configuration for it is fairly simple. It's the typical kinds of things that you set up for training a model, things like the number of steps and so forth. The ins and outs of it are a little more complex as well. So it's taking all these results from the upstream components that it got, and it's pushing to several different targets. But at the end of the day, it's just TensorFlow. So if you've worked through your code in a notebook, you can take that code and apply it in a production pipeline using Trainer. Evaluator is where we're going to really dive into the results, the performance of our model, and try to understand different slices of it. So things like model fairness, which is a big topic these days, or trying to understand critical segments of our data. Maybe it's critical segments of our users or situations where we need to make sure that our model generates a good result, even though it may be a rare situation where we have few data points. That sort of thing is the kind of thing that you try to understand by really diving into your model performance at the slice level. Model validator is really part of the productionizing of this thing. So model validator makes, what it does is you establish a criteria. And you say, don't push this model to production unless this and this and this. And usually this and this and this means it's got to be at least as good as the model that I have in production now. And there's no issues with particular slices or what have you. So that's model validator. Pusher, again, is where we really push out to our deployment target. So we've gone through the training process. We're satisfied that we've got a model that's good and we want to deploy it. Pusher is going to do the deployment. That's the configuration for it. Again, Python, really simple. Okay. So far we've talked a lot about TFX, TensorFlow Extended. And you have like some understanding at least of what it's all about. But how does this fit in with Flink? Well, we're going to talk about this a little bit. This is, wow. Okay. Sorry, I haven't seen that slide do that before. So this is Apache Beam, and this is the vision for Apache Beam. So the idea is you have a number of different languages that you can work in. Java, Python, Go, SQL. And you have an operation that you want to perform. And you have a platform that you want to run it on. So the idea here is kind of any to any. And some of these are in various stages of development, as you might imagine. So Cloud Dataflow is in production and has been running for a long time. Apache Flink is very good in Java, and it's getting pretty solid in Python too. Apache Spark is kind of a work in progress, and we're looking for, if we have any open source contributors here, I would love to talk to you. Some of these others, Apache Samsa is in a similar state where we're trying to build some momentum around an early set of code for that. And some of these others are more planned. It's Apache Beam, it's an Apache project. Part of that too is cross-language. So we talked about a front end of using various languages, but once you've written something in one language, wouldn't it be great if you could take that and invoke it from a different language? Well, it turns out with the portability framework, you will be able to do that. In fact, you can do that now with a lot of different things. Not everything, but a lot of things. So here's an example where we're running a transform written in Java from Python. I/O is one of those things. So I/O, reading from different sources, is considered a transform in Java, in Beam, sorry. And there's a lot of those in Java. There's not as many of those in Go or Python. So we're we will be soon having portability across those languages for I/O as well. And this is what we're talking about. So in Java, we have all these different, we have file-based sources that we can read from. We have messaging, things like Kafka. And we have a bunch of databases, things like Cassandra. And of course, the Google databases as well, BigQuery. So what does Beam, how does it model things? Well, to start with, there's the idea of per element. It's analogous to, in MapReduce, the map operation. And it's a parallel operation. So every item is processed independently. There's no, there's a stateless implementation. So this is pretty typical kinds of thing. So that gets mapped into whatever runner you're running on. That operation in Beam is mapped to it. So when you change runners, you don't change your Beam code. Your Beam code is the same across all those different runners. There's combine. So that's the reduce. So we're usually pulling things by key or segment. It could be stateful if you're doing streaming. So that's the abstraction that Beam uses to apply to the different runners. So you could be running on top of Spark, you could be running on top of Flink, what have you, or Google Dataflow. There's also windowing. So I'm sure you're all familiar with windowing. You could be doing a sliding window, you could be doing a tumbling window. You've got to worry about things like arrival times. So something is time-stamped as 8 o'clock, when did you actually receive it? You've got to get all that stuff marshaled. You've got to decide how you're going to deal with an individual window, all that stuff. So one of the other things that we have to fight with or try to solve are parallel execution problems. And you guys are probably all familiar with that if you're coming out of Flink. So in non-parallel, you're just waiting for everything to happen. In a perfect world, you split up your job and apply it across all your workers, and everything happens, and all your CPUs are busy all the time. But in the real world, mostly, you're waiting for the last one to finish. So you have a bunch of workers that are sitting idle, and you're waiting for one to finally finish so you can start the next one. So Beam has a way of dealing with this. It's called dynamic work rebalancing. And the idea here is that we're going to take a typical scenario like this, where we're waiting for the last one to finish. We're going to grab some of its data, and we're going to give it to other workers. And in that way, we're going to balance the work across our workers. This is the kind of result that you get from this. So instead of things like this, where we're waiting for that slow worker to finish, we have a situation like that where things are a lot more even. We have much higher utilization. That's the kind of thing that we want to move to. This is a work in progress. On Google Dataflow, this works well. On Flink, not so much. So it relies on something called liquid sharding. Liquid sharding is non-trivial to implement. But the idea here is fairly simple to understand. It's going to monitor the worker progress and identify which workers are the stragglers. From those stragglers, it's going to ask for part of their work, their unprocessed work. So it's given it this data, it's going to ask for some of it back. It could be part of a file, it could be a key range. It's going to then take that work and schedule it onto other workers that have available capacity. And it's going to keep doing that until that phase of processing is done. So the amount of work to give away, deciding things like where do I slice it, all that stuff, it's non-trivial. But it's very doable, and it works in Google Dataflow, and it could work in Flink. So we're hoping to encourage the community to try to work towards, and in fact it already is, the Flink community is already working towards implementing this. So how does Beam, we talked about the way that Beam abstracts the operations, how does that actually map into Flink? Well, the Pardo that we talked about, that parallel operation that's like a map, pretty solid, both in Java and in Python for both batch and streaming. Where we have some gaps here is down in the stuff we just talked about, the liquid sharding that we need to do dynamic work rebalancing. But for the most part, we're looking pretty good. So the map from Beam to Flink is pretty solid. How am I doing on time? Okay. So looking at the individual ones, the Pardo is, yeah, fully supported. We're good on that. And that's good because that's used a lot. The group by key, again, fully supported. Again, good because that's used all the time. Stateful processing, mostly there. There's some issues with non-merging windows in Flink. I don't think that's going to be the case for very long. I think they're going to solve that fairly quickly. And that's it. So at this point, I could take some questions.
Yeah, maybe we have time for 1 or 2 questions. Any questions? No.
All right. Well, thanks very much.
Thank you.